Started our discussion of statistics and went through a ton of vocabulary. So today I kind of want to recap one part of that and then continue on with it and how it affects us and what we've most of what we have seen before in organizing data. And so one of the things we talked about was that random variable. And we said that the purpose of any sort of statistical study is to ask a question. And the answer to that question is the random variable. And we said that random variable is broken down into two main types. Categorical, which a lot of textbooks refer to as qualitative, because it measures the quality of an item. And that's just when the answer to that question being asked is a category, with a favorite color or what major, what program you want to study when you go to college, things like that. Any yes or no question is categorical. And then numerical, which was in many textbooks called quantitative, because the answer to that question is a quantity. It's a number of some sort. And the numerical could be broken down in a couple of different ways. Discrete, where discrete was where it could take on specific values on an interval. And we said that the kind of one of the qualifications here is things that can be counted. And the other type of numerical variable is continuous. And a continuous variable takes on every value over a range. So where discrete variables may have gaps in between the values, continuous does not. No matter how close together two values are, there's always a value in between them for continuous variables. And we said these variables were typically measured. And we said one of the qualifications, because there are some gray areas between discrete and continuous, and one of the qualifications was rounding. If there is natural rounding, or whether we had to impose rounding. We refer to that as arbitrary rounding, where we actually had to decide what digit are we going to naturally round it to. Some examples that come into effect here. One is money. We mentioned this a little bit. It's natural to round to a penny. Or $0.01. Because of that, money actually can be considered discrete because you can count those pennies once you have that natural rounding. If you're calculating down to the millionth of a penny or whatever, you might do your calculations down to that, but it's still going to be reported to that nearest penny or hundredth of a dollar. Sometimes it depends on how you ask the question, like age. When we ask about age, there's actually a couple of different questions we could be asking. One of them, the most common one, is typically how many birthdays have you celebrated? So if you're 17, that's because you've celebrated 17 birthdays. But that includes everybody that's between 17 and 0 days old to 17 and 384 days old. There's a big range of people there. It's just counting the number of birthdays you celebrated. That would be discrete. But if the question were how long have you been alive, well, then this is now a continuous variable. Partly because you can't even get the answer out before the answer is changed. Before you finish the word, you've been alive for another part of a second. So there's some gray areas between the continuous and discrete. We're not going to get too deep into that in this class, but I wanted to point that out. If you were to go on to a more formal statistics course, it's not always as cut and dried and easy as it might appear. So we started actually in the last unit, we looked at large data sets, like picking a new school color, choosing between the red, blue, and green. And we saw that just having the raw data was hard to interpret. So this is just a list of all values. Or if it's a survey, all responses. And when we looked at that list, it depended on where we saw. Remember we talked about the human psychology of the brain, where our brain can really only take in between 7 and 13 items at once, and other things then kind of blur out around the edges. So when we're looking at that raw data, those responses, it depended on where we looked. If we looked at a spot where there's a lot of red responses together, our brain tended to think that, well, red is the most common response. If we looked at a spot where there were several green ones together, well, then we chose green. But when we actually organized the data, we found that the responses were almost exactly the same number for each color. So we want to look at summarizing the data a little bit more today. We've already seen how we can do it graphically. This is with the tables and, of course, the graphs that we saw in the last unit. And we put those data graphs in the last unit to kind of go along with the graphing. I'm going to assume at this point you all can read graphs. So we want to look at summarizing data numerically. So before we can accurately summarize data numerically, we have to understand what is it we're communicating? What is it we are describing with these numbers? What we're describing is something called a data distribution. And the best way to talk about a data distribution is to think of, well, use something called a dot plot. A dot plot is basically a number line that lists all possible values of the variable. So let's say we're looking at scores on a quiz that I've given to several groups of students, and the range of scores goes from 3 to 10. So we'll start numbering at 3, 4, 5, 6, 7, 8, 9, 10. So we number our number line for the full range of possible values of the data. And then we start looking at those quizzes. And let's say the first quiz we look at had a score of 8. So I'm going to put a dot at 8. The next quiz had a score of 6. So I put a dot at 6. The next quiz had a score of 5. So I'll put a dot there. The next one has another 8. So I'll put a dot above the other one. And I just keep looking at these quizzes and their scores and stacking up the dots on the graph. And you can see as these dots stack up, they form a shape. If I trace a line through the top dots in each of those little piles or columns or whatever, we get a shape like that. This is a shape that many of us have heard referred to as the bell curve. And statistically speaking, it's actually called a normal curve or a normal distribution. It's called that because in nature, that is the shape that data normally takes on. If we were measuring, if we gave you a task, let's say we wanted you to assemble a model, and we timed how long it took you to put it together. If we had you do that over and over and over again, the time it takes you to do it is not going to be the same every time. Sometimes be a little slower, sometimes a little faster. It would take on a normal curve like that, a bell-shaped curve like that at the times. If we measured height of students, again, the height of the students would take on that type of curve. Almost everything in nature takes on some sort of a bell-shaped curve like that. So if we wanted to describe that curve, oops. So I might start out with a curve that looks like this. If I was describing that curve, one of the things I might do is say, well, the middle of the curve is over the 5. Well, I might have another curve, green. Make it easy on myself by just tracing that one. I'll slide it over. If I had to describe the difference between the blue curve and the green curve, I'd say the blue curve is centered at 5. The green curve seems to have a center over 8. So they have different centers. So the center of the distribution, describing the center of the distribution, gives us some of the information about it. The other thing, comparing back to the light blue one again, they might have a distribution that looks something like that. That red one has the same center, but it's narrower. So this would be called the spread, or some textbooks would give it a fancy word called the dispersion. In other words, how spread out is the data? So now to explore these ideas of center and spread, I'm going to put 2 data sets here. Now, some vocabulary and some symbols, I should say, is the size of the sample. We had mentioned the other day that capital N is the size number of items in the population, small n is the number of items in the sample. So I'm going to put 2 samples down here. I'm going to put sample A, and I'm going to put 6, 34, 28, 8, 9, 12, 24, there's some more numbers in here, 23, 13, 14, 16, another 16, and another 16, 17, and 19. So we have what, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So I'm just going to make a note by that n equals 15. There's 15 numbers in that list. Now I have another list here, list B, and I'm going to put in the numbers 33, 30, 11, 15, 17, 28, 26, 24, 18, 21, another 21, and a 20. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 items there. So n equals 12 is the size of that list. If I want to look at measures center, there are 3 that we've all heard of, and there's a couple other kind of subsidiary ones. One of the main ones is the mean. The mean is what most of us have been calculating since about 3rd or 4th grade. It's just the arithmetic average. Find the average, we add them together and divide by how many are there. Now, if we let x equal each number, there's another symbol that looks like this called sigma, which means the sum, or add them up. So the mean is just the sum of all the values divided by n. Let's do that for set A here. So I'm going to add them up. I have 6 plus 34, which is 40, plus 28, which is 68, plus another 8, which is 76, plus 9 is 85, plus 12 is 97, plus 24 is 121, plus 23 is 144, plus 13 is 157, plus 14 is 171, plus 16 is 187, plus another 16 is 203, plus another 16 is 219, plus 17 is 236, and plus another 19 is 255 over 15. The 255 over 15 is, I believe that comes out to be 25, but let me, not 25, 17, something like that. 17 is correct. So there's our mean for data set A, 17. Let's find our mean for data set B. We'll add them all together. So we got 31, or 30 plus 33 is 63, plus 11 is 74, plus 15 is 89, plus 17 is 106, plus 28 is 134, plus 26 is 160, plus 24 is 184, plus 18 is 202, plus 21 is 223, plus 21 is 244, and plus 20 is 264. Did I add those all up right? I did not. Got 66, 74, 89, 106, 134, 124. Lost track again. Let me try that again. So 66, 74, 89, 106, 134, 160, 184, 202, 223, 244, and 264. So this is 264 over 12. Okay, so if we go to add those, or to divide that out, 264 divided by 12, we get 22. So the mean there is 22. So we have different measures of one measure of center is the mean. So you can see each of those data sets, add them up, divide by how many are there. Now I did purposely make these data sets so that the mean would come out to a nice whole number. Usually there'll be a decimal involved. Our second measure of center is called the median. And the median is the center. So it's literally half of the numbers are smaller than the median, half of the numbers in the center are larger than the median. So to find the median, we have to actually do several steps. Step one is to put the numbers in order. Usually we go smallest to largest. So I'll do this with data set A. I'll do 6, 8, 9, 12, 13, 14, 16, 16, 16, 17, 19, 23, 24, 28, and 34. So there's step one. I've put them in order. Step two is going to be to find the position of the median. And we do that by using n times 1/2, or 0.5. Because remember we said half the data is smaller, half the data is larger. My computer's locking up on me here. Go. So here we have n times 0.5. So n here is 15 times 0.5 is going to give me 7.5. Now since that is a decimal, we round up to the 8th number in the list. So my median is the 8th number in my list. So I got 1, 2, 3, 4, 5, 6, 7, 8. My median is 16. Now you notice my mean was 17. So the median is slightly different than what the mean was. They should be really close, and 16 and 17 are really close. If they're far apart, then it tells us some things about the data that we'll look at in a little bit. For data set B, we'll do the same thing. Let's put them in order. We have 11, 15, 17, 18, 20, 21, 21, 24, 26, 28, 30, and 33. So we do the same thing. Now n here equals 12. So 12 times 0.5 is 6. Well, since this is a whole number instead of a decimal, that means our median is between that number and the next. So this is 6. That means we're between the 6th and the 7th number in the list. So I go 1, 2, 3, 4, 5, 6, 7. Well, both the 6th and 7th number are 21. So between 21 and 21, technically what I would do is I would add those two together and divide by 2 to find out what's between them. Of course, between 21 and 21 is 21. Now, once again, the mean here was 22, so they're slightly different, but they are really close together. The third is the mode. The mode is the number that occurs the most often. So in these two data sets, data set A, if I go back here, 16 appears 3 times. 16 is definitely the mode for data set A. For data set B, 21 appears twice. That's the only number that appears more than once. So 21 would be the mode for data set B. And you'll notice that that's actually equal to the median for each data set. And in a good data set, this is the case. It should be equal to the median because the median is going to be where the numbers are gathered up in the middle. But many data sets don't have a mode. Many data sets don't have any numbers that are repeated. So the mode doesn't tell us much. So the mode is not a terribly useful measure of center. It's really mostly useful when we have one of two things. One, we have a very large numerical set. So here, n equals 15, chances are you're probably going to have a mode in a set that size. N equals 12, maybe not. But if you have like 50 or 100 values in the data set, you're pretty much guaranteed to have a mode in that data set. The second place where the mode is actually useful is categorical data. If we're asking, what color do you want to change the school colors to, you can't find a mean or a median of color, but you can find what color is selected the most often. You can find a mode. So the mode is really an alternative measure of center that's most useful in special circumstances, mostly for the categorical data. Another measure of center we run into is called the mid-range. So for the mid-range, we need some vocabulary. An abbreviation, min stands for minimum. It is the smallest value. Max is short for maximum, which of course is the largest value in each data set. So the mid-range is the minimum plus the maximum divided by 2. In other words, the average of the smallest and largest number in the data set. So for set A, the smallest number was 6 and the largest number was 34. We add those together and divide by 2. Well, 6 plus 34 is 40. Divided by 2 is 20. Now again, that's close. We had a median of 21 and a mean of 22. The mid-range is close, but a little bit off. For set B, we have the smallest number was 11, and the largest number was 33. 11 plus 33, actually that doesn't work out. Number for A, it was actually 16 and 17 were the median and mean. So 20 is actually quite a ways away for set A. But anyway, for B, 11 plus 33 is 44, over 2 is 22. This one does work out because we had a mean of 22 and a median of 21, so it's right in line with them. So here set A might be having some issues if that mid-range is so much different from our other measures of center. And so let's look at that. What if the measures of center are different? It's something we call a skew. So in a perfectly normally distributed data, we get a bell curve that's symmetrical, or as close to symmetrical as I can draw. Something like that. And so now here, let's put in the mean, or let's start with the mode. The mode is going to be the highest point on the curve, because that's the spot that occurs the most often. The value that occurs the most often, that's the mode. In purple here, I'll put in the median. Well, the median is in the middle. Remember we said half the numbers are smaller than the median, half the numbers are larger than the median. So since this is symmetrical, that would be right in the middle as well. It's the same value as the mode. And the mean, again, since it's symmetrical, will also be there. So for a perfectly normally distributed set of data, the mean, median, and mode should give us the same value. And the mid-range should be right there as well. But our bell curve isn't always symmetrical. This would be what we would refer to as skewed to the left, because the left side is stretched out. This is what we would refer to as skewed right, because the right side is stretched out. So let's look at our mean, median, and mode. Let's look at our mode. The mode is still the highest point on each curve, so right about there for each of them. The median, however, is, again, same number of values on each side. Half the value smaller, half the value larger. So since there's extra numbers on the left tail here, the median gets moved over a little bit towards the direction of the skew. Same would happen here. It's going on the other side towards the skew. And the mean would get pulled even further. We'll look at examples that show how the mean gets pulled over even further here in a minute. But before we look at an example, let's ask, what is the best measure of center? I've already kind of seen my opinion on the mode as being only useful in special circumstances. We can agree that the mid-range is a pretty rough measure of center. So it really comes down to the mean or the median. Most people would say the mean because there's a satisfaction here. One, it's a formula we've used since a very young age. It's how we found the average for as long as we can remember in most cases. And there's something satisfying about plugging the numbers into the formula, adding them up, and then dividing. That median seems just tedious of putting them in order and finding a position and counting or whatever. Some textbooks have you cross off the first and last till you get to the middle. It seems like more of a process than a math calculation, and it really is. But let's take a look at an example here of where the mean and the median come into play and how they relate to each other. The example I like to use is 1983, University of Virginia. They advertised that in 1983, the average starting salary for a graduate in their BS in marketing, Bachelor's of Science in Marketing, was just over $78,000 per year. That's pretty good pay right now. If you offered me $78,000 a year, I might not be here next week. In 1983, $78,000 was phenomenal. You look at the average high school teacher starting out right now, that's in the low 30s. Back in 1983, it was between $16,000 and $18,000. So $78,000 a year was a lot of money. But what they failed to disclose was that one of the graduates in that program was a man by the name of Ralph Sampson. And Mr. Sampson was 7'4" tall. He had played on the University of Virginia basketball team, and both his junior and senior year, he was voted as the NCAA Men's Basketball Player of the Year. Voted as the best college basketball player in the nation, basically. So he was drafted first choice in the NBA draft. Made millions of dollars that year, but he still graduated with a bachelor's degree in marketing. It takes a lot of $20,000 marketing graduates to average out a multi-million-dollar contract to $78,000 a year. In fact, Sampson was the only one to make over $33,000 that year. So $78,000 doesn't sound like a very good measure of center if only one value was larger than it and all the other values were a lot smaller. This was obviously a mean. The median starting pay or starting salary for those graduates was just under, I had the number here, where'd it go? 27,000, there we go. Which is actually still pretty good at that time, but it's definitely not $78,000 a year. The mean is what we call more sensitive to outliers. So they're that one really large number threw the mean way off, whereas the median didn't change a whole lot. So the median is what we usually consider to be a more stable measure of center. Let's talk about measures of spread for a minute here. Now I'm going to put two data sets up here for the measures of spread. Data set C, I'm going to put them in order just to make it easier on us. 11, 15, 16, 18, and 25 is data set D. Data set D is 11, 12, 16, 21, and 25. Now you can see both of those have 5 items in them. So both of them have n equals 5. We go to measure center. One of our first measures of center is the range. And the range uses those values we used for the mid-range. It's just equal to the maximum or the largest value minus the minimum value. Well, if I look at these data sets for C, largest value is 25, smallest value is 11. We get a range of 14. For data set D, largest value is 25, smallest value is 11. We get a range of 14. They both have the same range. Well, does that mean they have the same amount of spread? Well, let's compare. We'll use our tool here that we like, the dot plot. And so what I'm going to do is I'm going to put this top data set C, in green. So I have 11, 15, 16, 18, and 25. Oops, I got my 18 in the wrong spot. There's 18 and 25. Let's look at data set D. I'll put those in red. I have 11, 12, 16, 21, 25. Now, if I asked which ones are more spread out, I would say, even though they have the same range, the green dots they're kind of compact in the center. They're kind of packed in tight. Whereas the red ones are spread out pretty evenly across. I would say the red ones are more spread out. So to say that they have the same spread where the range is the same number does not give us the whole picture. So the number we want to use is something called the standard deviation. The standard deviation is also linked to something called the variance. They're described the same thing. They're actually different stopping points along the same formula. There is a formula for standard deviation, but I'm going to go ahead and go through the process. It's a 6-step process. Step 1 is to find the mean. So let's just do this for data set A. We had, or for C, I should say, 11 plus 15 is 26, plus 16 is 42, plus 18 is 60, plus 25 is 85 over 5, which is going to give us 17 is our mean. Step 2 is to subtract the mean from each number. So I have my numbers 11, 15, 16, 18, and 25. I'm going to subtract my mean of 17 from each. So 11 minus 17 is negative 6. 15 minus 17 is negative 2. And I realize I'm going a little fast right now, but we only have like 6 minutes left. 16 minus 17 is negative 1. 18 minus 17 is a positive 1. and 25 minus 17 is 8. Now these numbers here actually have a name if we were doing a formal statistics course here. They are referred to as the deviation, or sometimes the deviations from the mean. Step 3 is going to be to square those deviations. So negative 6 squared. Remember, on your calculator, you got to use parentheses or you're going to get an answer of negative 36. We know any number squared is positive. So negative 6 squared is 36. Negative 2 squared is 4. Negative 1 squared is 1. Positive 1 squared is 1. And 8 squared is 64. This list of numbers is referred to as the squared deviation. The reason we have to square them is over here. If we were to add these up, the total would always come out to 0 because they're the same distance below the mean in total as they are above the mean, because the mean is the middle. So that number, if we added them up, would not tell us anything. So we have to square them to get them all on the positive side. Step 4 is going to be to find the sum. In other words, add those all up. If we add those all up, now we get what, 106, I believe? And that is, of course, the sum of the squared deviations. Now, step 5 is where most of the mistakes are made. Step 5 is a little tricky, so I'm going to list it down here. Step 5, if the set is a population, so if I'm looking at, the grades in my algebra class, well, the whole class is the population. There are no other students there. There's no need to take a sample because I have all the grades. If the set's a population, you divide by n. Notice that's a capital N because of the size of a population. If the set's a sample, we divide by little n minus 1. The reason for that is if it's a sample, if we already know the mean, we had to calculate the mean early in the process. Once we've got all of the numbers but 1, the last number is determined. So the n minus 1 is what we call degrees of freedom. So we divide by that for the sample. Now there's a more in-depth, detailed, technical explanation of that, but for now that's what we're going to just stick with is degrees of freedom for now. So n minus 1, this is a sample. N equals 5, so n minus 1 equals 4. So that means we divide by 4. 106 divided by 4 gives us, what is that, 26.5. Let me make sure that's correct. And so this number is what we refer to as the variance. If you're to get into more advanced statistical analysis, that variance becomes an important number. Step 6, the final step, is to take the square root of the variance. So the square root of 26.5 is going to give us 5.15. So what the square root, the standard, and this is, of course, is the standard deviation. And what that standard deviation is telling us is, on average, the numbers are 5.15 units away from the mean. That's what that's telling us, is the average distance from the mean. If I were to do set D, we're running out of time here, so I can't, but if I were to do set D, we would see that it has a little bit higher variance. It's a little bit more spread out, a little bit higher standard deviation. For now, let's give you some homework. So a couple of pages I want you to look at. This first one's actually kind of review. Page 339 through 340. 1 through 9. I want you to look at all of those. Those are the data graphs. They were in the last unit, but I just want you to look them over to make sure you've seen them all and are familiar with all of them. Page 347 through 348. 1 through 9. I'll just have you do the odd there because this is calculating mean, median, mode, standard deviation, range. We don't need to do a lot of problems with those because I know those formulas get a little bit tedious. On a test, you'll notice I only had 5 numbers in my data set for the standard deviation. I would never give you more than 10 numbers in that data set on the test, just because I don't want to have you clogged up for 40 minutes doing one calculation. So with that, we are done for the day. You guys have a great weekend, and hopefully we'll see you all back here on Monday.